All right, good morning. Does anyone have any questions on homework 2? So let me quickly kind of scroll through this. So I guess, first question is just Boolean algebra. Review of 12. In the resources tab on Canvas, I posted just an article that talks about all different Boolean identities. So if you need a refresher on that, the article that I linked is really good. There's also other resources online. Review from 12. Won't spend too much time on this. Then there is this question about transmission gates and the current through each of these MOSFETs. Maybe a little bit advanced of an analog question for a logic design class. But really just this question is nailing in the point that CMOS only draws current on switching times and doesn't draw any current in steady state. We can go over this if you'd like. Then there's this question, building gates from muxes. And then this one is building a mux tree using Verilog. And then the last two questions are drawing flip-flop waveforms. Yeah, okay. Has anyone started the homework? Okay, question.
Yeah, I was interested in the charging one, like
Yeah. The transmission gate question?
Yeah.
Yeah, sure. Did other people have questions about this? Yeah. So starting out, the first thing that I would do, so let's look at these two transitions. So the first thing, remember that CMOS only draws power when it switches. So first, let's just find the steady state of this right here. And let's walk through maybe this first transition. So starting out, so if A is 0 volts, so A is 0 volts here. What is not A? 1. And then B, what is B? What is B? 1. And what is not B? 0. Thank you. Okay. So if we look at these transmission gates, so do we remember in what condition the PMOS is enabled? What voltage needs to be at the gate for PMOS to be enabled? Yeah.
When it's like tied to water.
Try the other one. 0. Yeah. So PMOSs are enabled when they are tied to 0. So for example, this PMOS, the gate is set to 1. So will this be enabled? This will be disabled. So starting out, we're going to do, this is going to be disabled. But starting out over here then, so now this PMOS is tied to 0. So is this enabled? Yeah, it is. This NMOS is tied to 1 volt. When an NMOS gate is tied to 1, does that mean that it is enabled? Yes, it does. So this is enabled. So that means that this transmission gate right here is a short. Okay? And so if we have this 1 right here, then what is our output going to be? 1. So 1 is going to come through here, and it's going to be on this output. Yeah. So starting out, this is what is going to be on the output, is this 1. Yeah. Okay. Does that part make sense? Okay. Yeah.
So for the NMOS.
Yeah.
So for E, for not B, that would be 0.
Uh-huh.
And for NMOS, isn't it enabled at?
Yeah, so in this case, so the NMOS is disabled because it is tied to 0. So just whenever you have an NMOS that is fed in 0 volts at the gate, then that means it is disabled. So in both those cases, so the NMOS is disabled because it's receiving 0, and the PMOS is disabled because it's receiving 1. So this whole thing is disabled. Yeah, and it's just something that you want to memorize. You will be allowed a 1-page cheat sheet on the midterm. You can Write that down, tell your friends. So yeah, something probably pretty good to put on your cheat sheet is just the function of like when NMOS and PMOS are turned on. Okay, cool. So starting out, so then this is going to be 1 volt. And okay, so let's assume that this is now at 1 volt. What is now the current through, what is the current through these two MOSFETs right here? Yeah, so the current through these is going to be 0. And one way that you can tell that they're 0 is because they're disabled, right? But now if you look at these MOSFETs, these are enabled. So what will the current through these MOSFETs be in steady state? What is it? So after the one is already charged up, the current through these is 0. Yeah. So if there's nothing being charged up, then it's 0 volts. And we can imagine that there's a capacitor right here. And the whole idea with a capacitor is it's kind of like a battery. It's just like have we charged up this wire to 1 volt? And the idea is like if we want to discharge the battery, then we would want to tie this now to 0 volts. So if we wanted to discharge it, then we would need to hook it up to ground. If we wanted to charge it, we would connect it to 1 volt. So that's how a capacitor works. And in order to charge and discharge the capacitor, it takes current. Okay, cool. So this is what is currently happening. But now when we receive this switch right here, so what value changes on the switching? Yeah, B changes to what? To 0. Yeah, okay. All right, I'm going to get rid of this side. So take any pictures if you need this. I'm going to delete this. Okay. Okay. Cool. So now let's do the exact same thing with B. So, okay, so A is 0, not A is 1, and B is 0, B is 0, not B is what? It's 1. Okay, so this PMOS right here is being fed in 0 to the gate. Is this PMOS enabled? Yes, it is. Okay, is this NMOS enabled? Yes, because it's being fed in a 1. So therefore, so this is enabled. If we look over here, so this 1 is fed into this PMOS. Is this enabled? No. 0 volts fed into the NMOS. Is this enabled? No, so this is good. Okay, what is the current then going to be through these two MOSFETs? Yeah, it's no current, right? Because they are disabled. But then we have these two, which is very clearly we have a 1 tied directly to 0. So that means that we're going to have this capacitor discharging through these MOSFETs. So we're going to have current flowing in this direction. But now the question is, well, what? So here I say, so there's strongly charging, strongly discharging, weakly discharging. Would we call this charging or discharging? Yeah, this is discharging, right? It's discharging the output. Okay. So there's the PMOS and the NMOS, strongly and weakly discharging. So remember, so this capacitor, it's as it's being discharged, what is going to happen to this voltage right here? As you discharge this, what's going to happen with the voltage? Yeah, it's gonna drain. It's gonna go down. So and then as the voltage goes down and down, and let's say you're at maybe like half a volt now, then now one of these two transistors is not going to be operating most efficiently anymore. So if you go back into notes from like day 1 of this class, do we remember which MOSFET like really expects to be hooked up to a full like 1 volt? Yeah, the PMOS, right? The PMOS is really expecting to be constantly held at 1 volt. And if it's not held at 1 volt, then we actually say that it's not running most efficiently. And so in this case, like maybe at time equals 0, perfectly at time equals 0, this PMOS is going to be discharging super well. It's going to be like fully, like maximum current through it. But then as voltage falls, what do we imagine is probably going to happen to this current? Yeah, the current. Yeah, exactly. Yeah, the current will also decrease. So after just like a little bit of time, the PMOS is effectively like not even going to discharge anything. So therefore, we would say that this PMOS is probably like weakly discharging, because it discharges it a lot right at the beginning, and then not so much as time goes on. Versus this NMOS. This NMOS works best when it's tied to 0 volts, which it is in this case. So that means no matter what, for the entire time of this discharging, the NMOS is going to be very strong. Yeah. Okay. So that is the solution to homework 2.2a. Yeah. Yeah.
So if we assume that, let's say we have an input charging the output.
Yes.
We assume that the input just stays at 1 volt the entire time, therefore like a PMOS would also provide a strong charge.
So what are you asking, I'm gonna erase this if anyone wants to take a picture of this right now. Erase it. Okay, 5, 4, 3, 2, 1. Okay, cool. Yeah, so are you asking like if maybe you had the case where maybe you had a 1 right here and then this was enabled?
Yeah.
But the output from the previous like cycle or something was 0?
Yeah.
Oh. Wait, what was your question then?
So let's say that the input is 1 volt and the output is 0 and you're charging the output.
Yes.
Would the PMOS provide a strong charging current?
Oh, exactly. Yes. Right. Because the PMOS works best, when it's tied to 1 volt. So no matter what, for the entire time, since it's tied to a strong 1 volt, the PMOS will be strongly charging up the capacitor. Yeah. Versus the NMOS, you can see it like it started at 0 volts. So it was running really efficiently at first, and then as the voltage creeps up and up, then the NMOS will start working less and less effectively. Yeah. Yes.
So what's an example of it like weakly charging or discharging?
Yeah, so this would be an example of it weakly charging. Let me make it a little bit clearer. Yeah, so let's say B was, so what would we need B to be in order for this to be enabled? Yeah, so B would need to be 1, and not B would be 0. Okay, so that would now enable this transmission gate, and if we currently have this 0, then the 1 is tied to this PMOS, so the PMOS is very happy. The PMOS has a 1. You can think like 1, like P positive 1, I don't know. You can also think of it as like pulling up. P means pulling up, meaning like pulling up to 1 volt. So it's trying to pull up to 1 volt, so this is working effectively, and so the PMOS will be strongly charging. And the NMOS will be strongly charging at first, and then it'll be weakly charging after just a little bit.
Oh, I see.
Yeah. Okay. Wait, another question. Okay, let's assume that maybe we had a transition where maybe starting out we had 0 volts. No, let's say starting out we had 1 volt. Okay. And then maybe now we've switched, and then now we have this case directly afterwards. So we've just switched from having 1 volt on the output here to now having these inputs. So we had whatever, A looks like a 0 and B is 1. So what current now will be flowing through these 2 transistors if we have this case? Yeah? Yeah, no current, right? Because we've already charged up this capacitor. So now there is 0 voltage difference between these. And so there's no current that happens through this. And this is like, this is an example of steady state where nothing, there's no current being drawn. Yeah. Yeah.
So if the gate was previously like open, like closed, I mean, like, and it's a short,
Uh-huh.
and then it turns to closed, that's also no current.
Wait, say that again?
So like in that case where you had a short, and then say like, I don't know, B was switched, so that
Yeah.
like an open,
Right.
that's just no current.
No current. And then you're saying this one over here?
Yeah.
Yes, right. Yeah, so if we start out where maybe this charges up, so we have a 1 here, right? And it charges, and then, oh no, and then B and A quickly flip. And now there's a 1 here, and now this has current. Then yeah, in this case, there will be no current through these transistors. Yeah. Okay, cool. Transmission gates really cool. I won't spoil for you what gate this is, but also think about what gate this is implementing. That is what this question asks. What is the function of this circuit? So say like, oh, like this circuit is a transistor implementation for the blah, blah, blah gate. So yeah, okay. Cool. Any other questions on this homework? I'll spend another 1 minute because we have a lot of other things I want to talk about. This one makes sense? Digital.js. Yeah, so I would recommend just plugging it into Digital.js online and seeing what happens. Try mixing things around, try playing with it, see if you can exactly like get this circuit on the output. It's really cool, the website, Digital.js online. I met not the creator of Digital.js Online, but I met one of his students recently, and he had a lot of positive things to say about his advisor. That was kind of fun. Yeah. Cool. Yeah, I think that's good. I want to quickly pull up now homework 3. Homework 3 was just posted, and homework 3 is going to be really, really great midterm prep. So this first question is another like sum of products question. This you don't need to simplify your answer, but it's going through some basic kind of operations just to really nail in some of the things that we've been talking about in class. Yeah, like inequality, operator, or less than or equal. Here's also a dynamic shifter. So the idea is that when you have this value right here, then if you want to shift it by like a variable amount, like you want to shift it by 0 or shift it by 1, 2, or 3, then you will have to implement this to figure out exactly how this is done. Then you also need to create a counter that freezes at the value 4. So this will use muxes and should be pretty fun. Cool. This question is pulled straight out of last quarter's final. So I guarantee there will be a very similar question on the midterm and the final. This is asking about just the timing behavior of flip-flops. So setup, hold time, clock to queue. Really try to spend a lot of time really trying to understand how this works. You can try playing around with the flip-flop visualizer website that I provided to see if maybe you can make some sense of this using the flip-flop visualizer website. Question 4 is more of the same. Okay, question 5 is about shift registers, which we will probably go over on Wednesday. Question 6 is talking about register files, where you have a decoder and then a large mux at the end, and you have all these flip-flops in the middle. We will also go over that, I think, on Wednesday. And then this question is talking about pipelining. And we will cover this a little bit today. The idea that you have some sort of like array of flip-flops. So this is a D flip-flop right here, a very common different symbol for a D flip-flop. Remember that D flip-flops usually, like the way we've been drawing them, is that you have like a clock and you have D, and you have Q. Well, in this symbol, it's just we put the clock symbol at the top, and then the D side is over here, and then the Q side is over here. So there's a very common other way of drawing flip-flops, and the idea is that you have all of these flip-flops right here. It's a bunch of flip-flops that are all feeding into whatever combinational logic you have, and then this will feed into the next flip-flop, and the next flip-flop, and the next flip-flop, until finally we're at the end. And so this is a concept called pipelining, because you can think of kind of each kind of stage as like the stage in like an assembly line pipeline. Okay, we are going to start going over this. Okay. So the first thing that I wanted to show you is a cell that, that I quickly just mentioned in the register file question, and it is what a demux or decoder is. So this is the symbol. So it's very similar to a multiplexer, but notice that it's like a multiplexer that's facing the wrong way. So the idea is that so you still have the select, but now you have the input on the short side of the trapezoid, and it's passing it in, and then on the output now you have multiple outputs, and you will kind of route. You can think of this as like a router. You can route through this data to whichever output you'd like. So if select was maybe, was 0 volts, then now data will be sent through to this side, versus if select was 1, then now data will be sent through to this side. Not as common of a circuit element as a multiplexer, but still good to know. And it is widely used in register files, which is a question on your homework. So that is good reason to understand this. Yeah. Okay, that's probably all I'll talk about it because it's pretty straightforward. I'm gonna grab some water and then we'll move on. And also, if you're interested in how this is implemented, I believe that people also implement this usually using transmission gates. If you want, you can try to figure out a good way to design one of these. I won't grade it, but if you find like a cool circuit that implements this functionality, maybe you can post it in Piazza, and I'll endorse it. I'll say like nice or something. So yeah, feel free to play around with this. See if you can find an implementation for this. Yeah. You could look in the Skywater 130 nanometer PDK that I provided in the resources tab. You could try to figure out exactly how they implement their decoders. If you want. Okay, anyways, move along. Great. So we're going to talk about multipliers. So in general multipliers, right, so you have some input, and you have 2 inputs, and what will happen is you'll take this first number, right, and then you multiply it by the first digit of the second number. And then for the next row, now you add it to the first number, but shift it over by like 1 decimal spot, and then times the next number. And then after that, then you have, now it's shifted over by 2, multiplied by the next number, and then finally you have shifted over by 3, multiplied by the last number, right? So this is this is the algorithm that I'm sure we're all kind of used to with multiplication. The idea that you just keep adding zeros to the end of it and then multiply it by whatever digit you're currently on, right? Well, it turns out that this algorithm actually works perfectly, exactly the same for binary. So now here is binary multiplication. So if we were trying to multiply the numbers 11 and 9, well, yeah, we can do the exact same thing, where now we have this top number, so 1, 0, 1, 1, and then after the next row, then we shift it over by 1, right? And the next row, we shift it over by 2, Next row, we shift it over by 3. And then we can take all of these multiplications, and then we can add them together, and then that gives us our multiplied result. So let's walk through it. So this up here. So we have 1 times 1, 0, 1, 1. Okay, good. And then directly below that, do we add these two numbers together? No, right? Because so we have this 0 here. So this 0, in a way, kind of just tells you, like, do we add it or do we not add it? Which is very useful because remember, so usually decimal multiplication is you have to perform this really long, difficult multiplication. It's like, whatever, 1-digit number times this 4-digit number. It's a very complicated thing. And this is called large radix multiplication, if you want the official term for it, large radix. But down here, it's really convenient because, yeah, it's just a yes or no. And when we have a yes or no circuit, what circuit would we imagine that is? Yeah, if. What is an if? As digital designers? Starts with an M. Mux. Yeah, right. So we could probably just imagine that this value right here could be the select of a mux. And either we add in this value or we don't add in the value, or we add in 0. Yeah. And so let's walk through it though. So okay, so we pull this down, so 1, right? And we can cross these out. So this, yeah, is multiplied by 0, so we're not adding this, we're not adding this. Okay, so now we add this one, and then we have this one, which adds to this. So what is this 1 plus 1 going to be? It's going to be 0, yeah, but it's going to propagate the 1 now right there. So now we have another 0, but then it will be carried right there. So now we have 1 and 1. So that is our result. In theory, that will be our product. Let's quickly convert this to decimal, just to double check. So, okay. So what is this number right here that I've just selected? This part, yeah, so this is 3, right? So we know that this is 3, okay? And now let's double check this. So what is this number going to be? So there's 1, 2, 3, 4, 5 zeros in front. Yeah, so I think this one bit is going to be 32. And then this bit right here, what is this going to be? Probably double 32, yeah, so 64. Okay, what is 64 plus 32? 96, yep, and then plus 3. 99, okay. Did we win? We won, okay, yeah, 99. Cool, so there we go. Okay, so what we could now imagine is that, yeah, maybe we have this circuit down here where just for every place we have this B, and it's either B0, B1, B2, B3, all the way up to B of n, and we have all these muxes, and if B is 0, then we add 0, but if B is 1, then we add in A, but specifically A shifted by like whatever place B is in. So here we shift it by 0, but here we shift it by 1 because it's B1. Here we shift it by 2 because it's B2. Here we shift it by 3 because it's B3. Okay, right. Okay, so this is how you can do multiplication. There was a question on your lab where you had to think of a way that you could do multiplication by just doing a bunch of additions. We could probably do kind of the same thing, right, as we just did right here. Let me go on a side kind of tangent. So if we were trying to add the number, so I guess, so usually B is supposed to be, or I guess, sorry. So what the question in your lab was, is it was like create a times 240 unit. That's what was requested of you in your lab. I won't do that because it's, that'd be cheating. But maybe I can instead have have us do a times 9 unit. So how would we convert this into a times 9? Okay, actually go and spend 30 seconds on that. Think of how we could kind of modify this to now turn this into a times 9 unit. Yeah.
Well, if you make the B inputs
Uh-huh.
9,
Mhm.
so like B0, 1, B1, 2, 0, B3, 1.
Yeah, so how do you, if we write out like B right here, what is 9 in binary?
1, 0, 1.
Yeah, 1, 0, 0, 1. Okay. Right, so you're saying, so B0, we can say is 1, right? So that means that will we take 0 or A? Yeah, cool, okay, right. So and then for B1, will it be 0 or A? Yeah, 0. Next one, 0, and then next one. Yeah, and specifically it's A that's shifted, right? And since B is like a hard-coded constant, we actually don't need these muxes anymore, right? We can just kind of get rid of these. Not only that, but we also don't even need to like add 0. We could probably just get rid of these entirely. Yeah, and now all that we have after this is just A, and then A shifted by 3. So that is a times 9 unit that we have just created. And we could imagine that we could do basically the exact same process now for this times 640. Yeah, okay. Cool, I expect all of you to get full credit on that question now. Okay, good. Questions? Yeah.
Sorry, I still don't understand how that's like a times 9 unit.
Uh-huh.
Like, what was it before?
Before it was, so this was a multiplier that could take in 2 like variables, like 2 numbers, but we simplified it drastically by getting rid of a bunch of muxes, getting rid of a bunch of additions. So now all that's left is just an A and then an A shifted. We're adding them together, and this result will give us as if we were multiplying by 9.
So why do you have one of the muxes on the bottom and not on the top?
Sorry, I didn't finish erasing. Yeah, thank you. Good question. Okay. Yes.
Okay.
Sure, yeah. Cool. So this is all great and everything, but we're still assuming that we have this multi-operand adder right here. This is not something that we have talked about yet in class, so let's talk about it. So before I get to that, no, come on. Oh, wait. Oh, I see. Got it. Yeah. Okay, so if we have maybe a 4-word adder, let's say like each input is maybe like n bits, right? Doesn't even matter. N, sure. Then now, how do we actually implement this? So there's a few different ways, but let's assume that maybe the only cell that we can use to implement this is reducing this down. Maybe we are allowed to have a single 2-input n-bit adder. Maybe this produces n bits. Yeah. So assume we have this. How can we create now a 4-input adder? Okay. Go and test that out. Go and try to draw one out, and work with the person next to you. And then once you and the person next to you have figured out a good solution, go and compare with the person behind you. There are a few different ways that you can do this. So I want to see if we can find all the different ways. Okay, go and begin, work with the person next to you. Try to implement a 4-input adder using 2 input adders.
So you get that one, and then you create another one, and then you have another one that add those two.
Oh, sure, okay. So you're saying, so you have 3 total, and then maybe you have it like in this structure where you have like 4 inputs right here, and then these 2 add together, and then we kind of like divide and conquer, and then pass these in like this. Yeah. Did other people do it this way as well? Yeah. I think this is a totally reasonable way to implement this. And what's really great about it is it's going to be really fast. And actually, it's going to be as fast as possible. You can't do any better than this using these cells. And yeah, the reason for that is because we are maximizing our parallelism. So at every step, we are working like as in parallel as we possibly could. There's never an opportunity that we missed where we could have been doing more work. Yeah. There is I don't know about an issue, but like maybe a consideration that you may need to think about. And that's that this is actually going to be fairly power intensive though. Especially like, let's say, okay, like clock pulse is incoming, Maybe these are all fed by flip-flops. And then, okay, our clock signal goes high. Now all of our flip-flops change their values, and then all of the data propagates through all of these all at once. And maybe, for a 4-input adder, not the biggest deal, but maybe we had like a 30-input adder or something. Now we're going to have 30 adders, or maybe 15 adders, all going in parallel. And that means that now we have tons of CMOS switching occurring. And so we're going to have incredible power draw. And so maybe there's a way that we can implement this that maybe takes a little bit longer time. It's kind of interesting. Like usually you think you want things to go as fast as possible in circuits, but actually sometimes you actually want things to go just a little bit slower to even out the power usage in your chip. Like you don't want just like huge spikes in power. You instead maybe want like kind of just like a gradual kind of curve in power. Yeah. Okay. So what is maybe another way that we can implement this that maybe takes just a little bit longer? Anyone? Yeah.
You could put them all in a chain.
Sure.
First add 2, and then add another one to the result of that, and then add another one to the result of that.
Yeah, I really like that. Yeah. So it's the idea that maybe instead of this, we instead have a chain. So maybe kind of yeah, something like this, right? Yeah. Where we still have 4 additions that we can do. So we have input, and then input, and then input here. So we have 4 adders. And yeah, and sometimes it may be the case that you want to implement your adder, your multi-operand adder, using this structure. Maybe this is not the slowest thing in your circuit. Maybe there's something else that's slower that's taking up all the time. Okay, that is, maybe there's something that's slower in your circuit that is causing your clock frequency to be slower. So it doesn't matter that this specific part is running slower because something else in your circuit is the slowest part. If that makes sense. Yeah. Okay. Cool. And so hold that down right here. So here are 2 different versions of the multi-operand adder. Let's assume that we have this 2-input adder that takes 10 nanoseconds to do. Okay. If we have this structure, how long will it take in the worst case for the data to propagate out to the output if we have a 10 nanosecond delay on each one of these cells?
30.
Yeah, this will just be 30, right? We just add them up together. So this will be 30. What about this structure? Yeah, this is just 20, right? Because it's just this added with this. You can think of it as like a layer of parallelism happening, and then you add it to the next layer of parallelism that's happening, right? So this would be only 20. Yeah. Let's say now we wanted to increase this to maybe an 8 input multi-operand adder, right? How would we do that? Yeah?
Just like add two of those like 4 inputs on top of each other. Like,
Yeah, well, sure. So what I was thinking is maybe just like every single one of these can now be just another adder. Or is this what you were saying? Or you were thinking of taking this whole thing and getting it? Yeah. So, but if you do it this way, what's great is now you've just doubled the number of inputs. Now every single one of these is going to have 2, and so now this is an 8 input multi-operand adder. And how long will this take?
33.
Yeah, this will take 30. Okay. Can we find an equation for the delay given a k input adder for this input right here? Or for this? Yeah. Yeah.
One.
Yeah, so I think it's is it floor?
One plus.
I don't think it's floor. But close. Yeah, so but you're onto it. Let me scroll down to the next page. Okay, so for a 2 input adder, we're assuming that it's 10 nanoseconds. For a 4 input adder, now it is 20 nanoseconds. For an 8 input adder, how long was this? 30 nanoseconds, yeah. Okay. So it looks like, so as it increases, so it looks like it increases with the log, specifically log base what? Yeah, log base 2 of k times 10 nanoseconds. Okay, but now let's say maybe we had a 7 input adder. What will our delay be? Yeah, I think it's still 30, right? So if we had a 7 input adder and we just, got rid of that input, right? Then now there's 7 inputs, but still like the maximum parallelism that can happen is still 3 whole layers right here. There's 1 layer right here, another layer, another layer. So there's still, 3, we still need to wait at least 30 nanoseconds. So therefore, instead of the floor of log 2, what should it probably be? Yeah, the ceiling, right? And the ceiling is denoted with this syntax right here, if you've seen this, where you have like the brackets up top. Yeah. Cool. All right. This is a great final question, or midterm question, by the way. It's like, if you, start by drawing a 8 input multi-operand adder. Add a 9th input. Now how long does it take? Okay, wait, so if we now made this be, instead of a 7 input multi-operand adder, what if we wanted to now make it a 9 input adder? How long would that take? Yeah, I think it'd be 40, right? Because now we'd bring this back, but now we would need a full another layer of parallelism. Like there'd be no way that we could avoid a whole nother layer. Yeah. Okay. Think about that. Yeah. Okay. So fantastic. Okay. So let's say now maybe we have totally reasonable. So actually, I'll give you a little side tangent. So currently right now, I am working on building a linear algebra unit in Verilog, and we have the case where we have these massive arrays that are like 1,000 elements wide, and we need to perform addition on all 1,000 of these elements. And so what we'll have is like a 1,000 wide multi-operand adder. And if we, there's no beating around the bush, even if we're really using like an efficient layout, it's still a lot of logic being created, and it's going to be pretty slow. If we had a 1,000 input multi-operand adder, how long would that take if we assume that each adder was 10 nanoseconds? What would that be? Is it? What is log base 2 of 1,000? Is it 11? 9? Okay. Yeah, thank you. Oh, so 10, right? If we round it up. So if we now have that it takes 90 nanoseconds to add up 1,000 elements, and also that's taking up a lot of power, which isn't great, yes, whatever. So now our delay is 90 nanoseconds. And let's say this is part of like some multiplier, right? So let's say that now this whole thing, maybe if we factor in the muxes as well, maybe it's like 95 nanoseconds or something to do all this. Okay. And now let's say also maybe, so we have flip-flops on this. Maybe we have a 4 nanosecond setup time, 4 nanosecond clock to Q. So that means that clock to Q, right? So when you raise the clock input, then now the delay for this Q output to be valid takes 4 nanoseconds. And then it propagates through this. And I'll change it. I'll make it easier. So maybe now it's 92 nanoseconds. Let me modify this. Yeah, whatever. Assume 92 nanoseconds, okay, 92 nanoseconds. And then at the end, then the setup time is then 4 nanoseconds. So in the end, what is the minimum clock period that we can have to ensure that our circuit still works? What is our minimum clock period? Yeah, 100, right. You just add up all of these delays. Okay. What would this be converted to a clock frequency? Yeah, so if we do 1 over nanoseconds, you can also think of this as this. You can also think of this as if we wanted to convert this to microseconds. How many microseconds would this be? Yeah, so 0.1 microseconds. Okay, and what is 1 microsecond converted to clock frequencies? If you have a period of 1 microsecond, what would the clock frequency be? Yeah, it would be megahertz, right? But we remember, so we are now 10 times faster than 1 megahertz. So what would now the clock frequency be? Yeah, it'd be 10 megahertz. Okay. That's not a great number, right? 10 megahertz. What speed do things usually run at? Yeah, maybe like a gigahertz. On the FPGAs that we're using in class, we're using kind of very basic FPGAs. The maximum speed that you'll probably ever get is about 1/10 of a gigahertz, maybe faster if you're doing kind of magic stuff. So we're not going to get super fast, but 10 megahertz is kind of laughable. Like if you came along and you're like, hey, like I designed the circuit, it runs at 10 megahertz. People, you get fired. Like no, it's not a great look. Even 50 megahertz is still not great. You want to be as close to like 100 megahertz as possible in general. So okay, well maybe there's some sort of optimization that we can do, and I'm going to modify this that I prepared. So let's say now. So this is what our circuit currently looks like. Effectively, right? I guess I'm missing some muxes, missing some stuff, but this is kind of the most important things. Let's assume that this is what our circuit looks like. How can we now increase our clock frequency? Not necessarily make this run any faster, right? We've already figured out that this is basically as parallelized as possible. Like we can't do any more work, but maybe there's a way that we can at least just make our flip-flops run a little bit faster. Like how can we speed up our clock frequency? Yeah. So go and take a second. So how can we speed up clock frequency? Maybe not actually speed up the propagation, but yeah, okay. So take 20 seconds. Maybe share it with the person next to you. How can we speed up clock frequency? Do you have a question? Okay, yeah. Yeah, go and tell the person next to you. If they disagree, then fight them. Okay, so, yes. So in order to find out the clock frequency of this, what are the 3 delays that we need to add up? Do you remember? Yep, setup time, clock to queue. What's the last one? Combinational delay, yeah. So our setup time and clock to queue, that is unfortunately fixed with whichever PDK we happen to be stuck with. If we're using the Sky 130 PDK, then maybe our setup and clock to queue, maybe it's this. I guarantee it's a little bit faster than 4 nanoseconds, but maybe it's that. And then maybe our combinational delay. So what is our combinational delay through this circuit?
20.
Yeah, it's 20. But this is not technically fixed, right? We could try to decrease combinational delay. How can we do this? Yeah.
You put a mux right in the middle, and then you can work on 2 numbers at the same time. And it not quite happens here.
A mux right in the middle?
Or not a mux, sorry, a flip-flop.
Oh, yeah, okay, yeah, no, I'm totally on board with you. Yeah, well, so maybe, we could just insert a flip-flop right here. And if we do that, well, now look at what happens to our combinational delay. Now, it comes out of the flip-flop, right? We have clock to queue now, then it goes through combinational circuit. Well, what is the delay of our combinational circuit? Yeah, it's only 10 now, and then now it's the setup time, and so now we've almost cut our propagation delay in half. Now, like before, it was 28, but now we've just decreased it to 18. So it's significantly less. And so this is the whole idea with pipelining. This is called a pipeline stage that we've just inserted. It's the idea that you can just put a flip-flop right in the middle of your combinational delay, and now your clock frequency can be increased. So notice that unfortunately we do add a little bit extra delay here, right? Because our clock to queue is 4 nanoseconds, setup time 4 nanoseconds. So actually adding this flip-flop actually will slow down your design just a little bit. Looks like it'll overall slow down your design by at least like 8 nanoseconds, if not more. So yeah, it's not perfect. Like if you're wanting it to be as fast as possible, there technically are faster ways that you can do this. But this is definitely the most popular way of just like brute force speeding up your clock frequency, add a pipeline stage. And then maybe at the end of it, maybe you just know like, okay, like, this circuit, maybe we call this circuit like, I don't know, adder for whatever, CSE100 or something. Like we gave this circuit a name, and then in the data sheet for it, we just specify like this circuit will take an extra clock cycle or something. It'll take maybe a total of 3 clock cycles, one for the input, and then one for an intermediate pipeline stage, and then one for the output. So maybe we just say that, and so now people have the responsibility now to use your circuit effectively. So it's yes, it will kind of mess up the maybe before, like if people were expecting the design to work like this, it now will operate a little bit differently because now they'll need to wait for another clock cycle. Yeah. Okay. Does that kind of make sense? Right. Yes. Question.
Yeah, I'm sorry, how does it make it faster?
Yeah. So it's decreasing our combinational delay, because before it was 20 nanoseconds to go from this to this. Now it's only 10 nanoseconds to go from one flip-flop to the next flip-flop. So so we're only looking at just like the time for a flip-flop's data to be sent to the next like endpoint. So the maximum clock frequency that we can run at now and still have things arrive at the next flip-flop is we've now made it so that it can arrive at the next flip-flop like faster than before. Like before it needed to wait longer, but now it doesn't have to wait as long. So our clock can be faster. It can sample faster. Yeah. And also, yeah, remember that all of these flip-flops are all connected to the same clock. So they all, like when we increase our clock frequency, we increase it for all of these flip-flops. Yeah, question.
Could you say like increases your bandwidth of the thing, like it increases the number of operations you can do every second, even if each operation takes as long?
Yes, and that is, I won't get into that right now, but yes, actually there is a question on your homework that will kind of get into that. Yeah, I won't get into that at the moment though. Yeah, another question.
For the flip-flop, would it be 2, or would the flip-flop just take it 2?
So each of these like long flip-flops, this is just another symbol to mean actually just like a bunch of flip-flops. Yeah, so here there's a register right here, and then here's a register, and then here are like, 4 whole flip-flops right here. This is actually only 1 flip-flop. Yeah. Yeah, and like if we wanted, like, we could extend this out if we had like a bunch of flip-flop stages. Right. So in like modern processors, you might have anywhere from 4 to 20 pipeline stages in any like individual like cell that you have. So you will have like, it's like maybe you're doing some sort of logic here, and then doing logic here, and doing logic here, and then through each of these stages it propagates through. Because originally, like it would have been a very long amount of time if you wanted to perform all of this combinationally in one single clock cycle. But now you can perform just little chunks of it. And so now your clock frequency goes up. Yeah, another question.
You said implementing like that pipeline would overall be slower. Like, can you explain why that is?
Yeah, so I think I'll talk a little bit more on pipelines on Wednesday. Yeah, but the whole idea is that now you have to factor in all of the delay introduced by all these flip-flops. So your clock frequency goes up, but still the amount of like circuit that your signal needs to propagate through is actually increased. So now like your data needs to propagate further and further. So your total latency, latency is the term for like how long it takes for your output to be generated. Your total latency will go up, because there's just more to go through. Okay, thank you so much, everyone. That is all we will talk about. We will talk more about flip-flops all this week.